Okay, so have you ever just stopped for a second and wondered what everything is actually made of? I mean, your phone, the air you're breathing, even the stars. It just seems so impossibly complex, right? But what if I told you it all boils down to just a handful of basic building blocks? Well, that's what we're talking about today. So let's dive into the universe's ultimate construction set. No, seriously, think about it for a second. What if this entire, unbelievably complex universe was just a giant Lego set? You know, built from a handful of basic pieces, with a simple little rule book that shows how they all snap together. Well, guess what? That's pretty much the core idea behind all of chemistry. And today, yeah, we're going to become master builders.
So yeah, this is the official rulebook. Chemistry, it's the branch of science that studies matter. It's all about figuring out what all the stuff in the universe is, what it can do, and this is the important part, how it changes and interacts. It is literally the instruction manual for our cosmic Lego set.
And I know what you're thinking. Matter. That sounds like a super scientific, kind of intimidating word. But I promise you, it's not. Just look around you, right now. The chair you're on, the air, your phone, that's all matter. And all of that stuff is just a giant collection of tiny, tiny pieces that are always moving, always vibrating, always bumping into each other. All right, so if we're going to be master builders, the first thing we need to do is get to know our pieces, right? I mean, every good construction set starts with the basics. You got your individual bricks, the things you build with them, and of course, the box you keep them all in. Okay, let's start with the most fundamental piece in our entire kit, the atom. The absolute easiest way to think about it, it's like one single Lego brick. It is the smallest possible unit of a substance you can have. That's it. You can't break it down any further. This is the bedrock. Right. So what happens when you get a whole bunch of the exact same type of atom all together in one spot? Well, then you've got yourself an element. So if an atom is one red Lego brick, an element is like having a giant pile of only red Lego bricks. You know, think about a pure copper pipe or an old penny. That's an element. It's made of trillions and trillions of identical copper atoms, and nothing else.
Okay, now this is where it starts to get really cool. This is where the building begins. A compound. That's what you get when atoms from different elements link up together. And I'm not talking about just tossing them in a pile. No. It's like taking a red Lego brick and a blue one and getting that satisfying click when they lock together. That click, that's a chemical bond, and it creates something brand new. Like taking two invisible gases, hydrogen and oxygen, clicking them together and getting liquid water, H2O.
But what if you don't click them together? What if you just dump all the pieces into the same toy box? Well, that brings us to mixtures. A mixture is when you've got different things just hanging out in the same place. But, and listen up, this is the most important part, they are not chemically bonded. They haven't clicked. They're just sharing the same space. Kind of like a jumble of Legos in a bin. Or trail mix. You can still see the M&Ms and the nuts, and you can totally pick them out, right? Because nothing has actually changed. So let's just nail this down. Compound versus mixture. This is the big showdown. With a compound, the pieces click together chemically to make a totally new thing. With a mixture, they're just tossed in the same box. They're blended, not bonded. That's the key phrase right there. Blended, not bonded. All the pieces just stay as they are. And here's a little cheat sheet to kind of put it all together. Super simple. You've got your elements, which are pure, like copper. You've got compounds, which are chemically bonded, like water. And you've got mixtures, which are just physically blended. Think salad dressing. Pure, bonded, or blended. That's it. If you can remember that, you've totally got this.
Okay, we know our pieces. We've got our atoms, elements, compounds, and mixtures. So now let's talk about the different neighborhoods they can live in. We're going to explore the three main states of matter: solids, liquids, and gases.
First up, let's talk about solids. The best way to picture a solid? Imagine a packed movie theater. All the molecules have assigned seats, and they're packed in there tight. Sure, they can kind of fidget in their seats, vibrate a little bit, but they can't just get up and swap places with the guy in the front row. That's why solids have a fixed shape. Now, a liquid? That's a whole different vibe. A liquid is more like a crowded hallway between classes. The molecules are still pretty close together, but now they can slide and weave past each other. Excuse me, pardon me, coming through, And that's why a liquid can flow and take the shape of whatever container you pour it into.
And finally, we've got gas.
So if a liquid is that crowded hallway, a gas is like a giant game of tag in a huge open park. These molecules have so much energy they've just completely broken free from each other. They're just zipping around way far apart and they'll expand to fill literally any space they're put in.
So the big question is, how does matter move between these neighborhoods? How does a solid melt into a liquid? The secret ingredient is energy, usually heat. It's a really simple chain reaction. Step 1, you add energy. Step 2, the molecules start vibrating and moving way faster. Step 3, the attractions holding them together get weaker. And step 4, boom, they break free. That's a phase change.
Okay, so we've covered what matter is, but now how do we actually know all this stuff? How did scientists write the instruction manual for our cosmic Lego set in the first place? Well, they have a system, a kind of rule book for how to figure things out.
And that system is, of course, the scientific method. It's not as scary as it sounds. It really just starts with being curious. You ask a question. Then you do a little research to see what other people already know. After that, you make an educated guess. That's your hypothesis. And then comes the fun part. You design an experiment to test if your guess was right. You look at the results, figure out what they mean, and then you tell people what you found. It's just a logical way to get a reliable answer.
All right, to make this whole thing less abstract, let's put it into action. Let's solve the case of the constantly replaced goldfish. Imagine a science class has a goldfish, but it keeps not making it. So the class asks a question. Why does our fish keep dying? They form a hypothesis. Maybe we're not feeding it the right amount. So they decide to design an experiment to test just that one thing.
Now, this is super important. To run a fair test, you have to make sure you're only testing one thing at a time. Everything else has to stay the same. We call these constants. So if you're testing the amount of food, you have to use the same type of fish, the same size tank, the same water, the same temperature. Everything else has to be identical. Otherwise, you won't know if it was the food that made the difference. So once you have your constants locked down, you're left with just two variables. First is the independent variable. That's the one thing you change on purpose. In our case, that's the amount of food. The second one is the dependent variable. That's the result that you measure. Here, it would be the health of the fish. Just think of it like this. The independent variable is the cause, and the dependent variable is the effect. Simple as that.
Okay, we are almost there. This is the last, but super crucial part of the scientist's rulebook. When you're running your experiment and collecting data, your measurements have to be good. And to know if they're good, you need to understand two key ideas: accuracy versus precision.
And honestly, the best way to get this is the dartboard analogy. It makes it so clear. Accuracy is how close you are to the real, true value. So on a dartboard, that means hitting the bullseye. Precision, on the other hand, is how close your measurements are to each other. That's like throwing 3 darts and having them all land in the exact same spot, even if that spot is way off in the corner. See the difference? And in science, of course, we're always aiming for both. So how do you actually measure your accuracy? Well, scientists use a little tool called percent error. Now, I know that sounds like scary math, but it's really not, I swear. It's just a super simple formula that tells you exactly how far off your measurement was from the known correct answer. You just subtract, divide, multiply by 100, and bam! It tells you how close you got to hitting that bullseye.
And that's it. With that, you now know the fundamental rules of the entire universe's construction set. You know the pieces, the neighborhoods they live in, and the rulebook for how we figure it all out. So I'm going to leave you with one final challenge, Master Builder. Just look around you right now, wherever you are. Based on everything we just talked about, can you spot one element, one compound, and one mixture? I bet you can. Give it a shot. You'll start seeing the chemistry in everything.